Right, let us continue with the revision of hydrocarbon. Now, see what are the other reactions we need to learn. One is oxymercuration, oxymercuration, demercuration. Okay, demercuration. What is that you need to know? Let me show you with an example. Suppose if you have an alkene like this, and imagine if at all I am treating this with uh, HgOAc twice in the presence of water, and then I'm using NaBH4. So the first part is oxymercuration, the second part is demercuration. Now this will lead to the formation of a secondary alcohol. Okay, so basically here you will notice that mercury will make a bridge. This is one thing you should remember. And then water as a nucleophile will attack on the more substituted side. So there is no carbocation formation here. So Hg will become plus here. So as it takes electrons, it will become Hg, and BH4 minus will attack here as a nucleophile, bringing H minus. So this is how it will happen. So the important points that we need to note in this case implies. So we will get this alcohol here. Check out what are the important points to be noted here. First thing, there is no carbocation and no rearrangement. And this is non-stereo specific reaction. Got it? It is following Markovnikov addition. So Markovnikov addition is followed. So these are the important points you need to know it from oxymercuration, demercuration. Okay. Similarly, we have hydroboration and oxidation reaction. Hydroboration and oxidation reaction. I will take the same molecule here, try to react that with first B2H6 in the presence of THF, followed by H2O2 in the presence of OH minus. Got it? Now in here, what would happen? First, the product, let me write down. So you will get OH being added here and H being added here. Mechanism wise, if you notice, what are things you need to remember is that there will be a 4-membered ring like this. So hydrogen is connected to that of boron here, which already has 2 hydrogens this way. This is the 4-membered cyclic transition state which is formed. So from here it is clear that H is getting added onto the more substituted side. And this way the bond will break here and this bond will break here. So you will get hydrogen getting added, and thereafter OH minus will get added onto this position. Okay, so this is the only factor you need to know from here. Okay, so if you have something like a trialkyl group like this, if boron is connected here like this and boron is connected like this, correct? This is trialkyl boron, and this with 3 moles of OH minus in the presence of H2O2, this will lead to formation of 3 moles of alcohols. Okay, and BO3 3 minus. These are the products you will get. Interesting thing what you need to notice here is this alkyl boron R3B. If you react that with H2O2 in the presence of OH minus, that will lead to formation of alcohols. But in case if at all we make the reaction in acidic medium like CH3COOH, then we will get 3 moles of alkane. Okay, and if you react that in the presence of AgNO3, correct? Sorry, silver, in the presence of silver and heat. Now this will become and R, which is the coupled product here. Okay, so just remember what medium you are using, correct? What are the important points here that we need to note? This is a syn addition. Okay, so this is a syn addition or syn stereo specific. There is no carbocation, there is no rearrangement, clear, and it is following anti-Markonikov's rule, anti-Markov rule. Got it, right? So this is about hydroboration. Uh, Last one being a simple hydration, which is acidic form. So if I take the same thing here, same reagent, same reactant here, and if I treat this with H3O plus, it meant that you are supposed to do protonation and finally get the alcohol here. How is that? The pi bond will attack on H plus. Following Markonikov's, it will get a carbocation. That carbocation will undergo rearrangement, and finally water will attack on this position, and that's how we will get an alcohol form. So what we are getting is a 3-degree alcohol. In the whole, if you notice that we are getting a 3-degree alcohol here, we are getting a 1-degree alcohol here, and in here we were getting a 2-degree alcohol. Okay, so depending upon what is being used. What are the important points that we need to know in the simple hydration process? Here it is, uh, here the hydration is uh, carbocation formation. So there is a carbocation forming. So whenever there is a carbocation forming, chances of rearrangement is always observed. And this is also non-stereo specific, and it is following Markonikov's rule. Markonikov's rule. Okay. So these are the important pointers that we need to know it from hydration reaction. So all these three are hydration reactions. Suppose a very standard question that is being given in this area is this one. Check out. If a question is being given like this, where a double bond is present and oxymercuration demercuration is being made, then definitely addition would happen according to Markonikov's rule. So only one product will come. So you can see only one product will come here. On the other hand, if you get HBO reaction, then you will get an OH group here. So, but one thing is that H and OH should be added from the same side. So, which means if methyl is here and hydrogen is going inside, then OH has to be inside as well. Okay. Or the other way around. So, if hydrogen is outside and methyl is inside, then OH here also should come outside. Okay. So, both should be syn to each other. So this is the syn addition, and both of them are enantiomers of each other. So therefore 50% and 50% will be formed, giving it to be a racemic mixture. This is a very standard question. So make sure you are aware of this part. Clear? This is about simple hydration. Next one is KCP versus TCP products. Okay, this is one small scenario that you need to know, wherein if you have a double bonds this way, okay, conjugated double bonds, then you are making an HBr addition in the presence of CCl4, but only one equivalent. Then there are two products I can get, one H getting added here, Br getting added here with a double bond remaining here, or I can also get double bond here and Br getting added here. Okay, this one is called KCP, this one is called TCP, kinetically controlled product and thermodynamically controlled product. Okay, this would be usually major at minus 80 degrees, and usually at minus 80 degrees or up to minus 40 degrees you will see this. And anything 0 degrees up to 20 degrees, 80 degrees, all of that, this is major at 80 degrees. Okay, clear? I'm not getting into the mechanism of it. You just need to remember this way. It is a 1-2 addition, while this is a 1-4 addition. Okay, following Markovnikov's rule, it is 1-2 addition and 1-4 addition. Correct. Next, we have Kucherev's Kucherov's reaction. Kucherov's reaction, I told you this earlier also, that if you have CH3, C triple bond CH, and then you treat this with Hg2 plus salt with dilute H plus. In that case, you will get an enol type of formation here with OH and CH2 following Markov addition. So following Markovnikov addition, this is what you will get. Once you get that, it will undergo tautomerism to convert into keto form. So you should be going towards the more stable side, more stable OH group side. So this will be the major yield, correct? One standard question that has been asked from this area is like this, where you have a double bond here with Hg2 plus and dilute H2SO4. In that case, the major product has to be on the phenolic side. But if you have like this triple bond here, like this, okay, so one side there is a methyl, one side there is a ethyl, and let's say I have given you HgSO4 and dilute H2SO4. In that case, chances of this ketone and chances of this ketone are almost 50-50 percentage. So here you cannot differentiate so much. Correct? So these two examples are important. So please make sure you're aware of this part. This is about Kucherov's reaction. Next one is hydroxylation. Hydroxylation is addition of two OH groups. Got it? Suppose if you have a cis alkene, correct? And then you are treating this with alkaline KMNO4 of 1% cold and dilute. So then the cis will undergo a syn addition. This will go via syn addition here. Through syn addition, you should be able to get erythroforms. So like this. So we will get to methyl and methyl here, OH and OH here, H and H here. What are the important points you need to know from here? See, manganese, which was MnO4 minus here, will convert eventually into MnO2. Okay, a precipitate, a black brown precipitate, changing its oxidation state from +7 to +4. So making 3 electrons transferred here. Got it? So important points in this case, what is that to be noted? It is a syn addition. That's a most important point. Next, also known as glycolization, because you're making it in glycol form. This is called Bayer's reagent. This is called Bayer's reagent. Okay, it is used for test for unsaturation. Test for unsaturation. Clear? Color change is from purple to brown. Purple to brown. Okay. Brown precipitate with colorless solution. That's it. Okay. This is about Bayer's reagent. Okay. It will go for a syn addition. That is one thing you should know. Similarly, if you have, let's say, trans, and then I use first osmium tetraoxide in the presence of NaHSO3. Got it? So in that case, this is a trans molecule, but osmium will also give you a syn addition. by which if you notice that trans plus syn is being made, then you will get an 3O product. So which means you would have like this with methyl and OH on the other side. So it could become racemic mixture here, OH and OH, like this with H and H here, H and H here. So what are we getting? This is a uh, 3O form. If this is plus, which means it is dextrorotatory, the other one has to be levorotatory. If this is 50%, the other one has to be 50%, making it as racemic mixture. Making this as racemic mixture. Got it? What are the important points need to be noted here? Check it out. First, osmium tetroxide. This is also a syn addition. Clear? Here, osmium with +8 oxidation state is changing to osmium at +6 oxidation state. So, 2 electrons are being transferred in this case. Clear? And uh, here, there is nothing to do with the color. So, it is not a test for unsaturation, right? So, these are the 2 pointers we need to know. Next one, suppose if at all I take another syn molecule here like this, correct? And then I treat this with any peroxy acid. Got it? Any peroxy acid. Most used is MCPBA, meta chloroperoxy benzoic acid. So first you need to do this, then followed by hydrolysis. And as you do this part, you will get OH and OH on the opposite side like this, which means it is a 3O product. This is a 3O product, same as what we got above. Correct? But this time the addition type is anti. Overall reaction is anti-addition. Anti-addition overall. Correct? What do you mean by overall? Here there are 2 steps. So what are the steps here? First, when you react with MCPBA, there will be an syn addition. So you will get this product first. So this is syn addition. And since you are adding only single oxygen, this is called epoxidation. So it is called syn epoxidation. So basically MCPBA is a syn addition, and that is the first step. The second step, when the hydrolysis happen, that will be an anti-hydrolysis. Anti-hydrolysis. Got it? That's how it becomes an overall anti-addition reaction. Okay. Now what is to be noted here is, in case if you have something like more bulkier substitute form like this and unsymmetrical epoxide, and that when you react with H3O plus, so first protonation will happen at this position like this, and thereafter H2O will attack on the more substituted side and breaking this bond, and thereby you will get this as OH here, and another OH got added here like this. Okay, so in case if this oxygen was something isotopic, then this is where the isotopic oxygen will remain. But if the same reactant is in the basic medium, if at all it was in basic medium, let's say OH minus is here, then the attack would directly happen on the least substituted side. So OH minus will attack here, bond would break, and you will get this as O minus, and here you will get this as OH, followed by hydrolysis. So you will get this as OH, and here you will get this as OH. Clear? So here if you notice, this is the oxygen which is isotopic form. So that's one important point that you need to notice when it comes to anti-addition. Clear? Next. If it comes to reactions with NBS, N-bromosuccinamide. Okay. Basically, we are talking about an allylic reaction. By structure, if it is been asked, N-bromosuccinamide is like this, N and Br. This is N-bromosuccinamide. Let me write down that N-bromosuccinamide. Okay. Now this is the best source of Br at allyl positions. Br dot at allyl and benzyl positions. This is the best source for allyl and benzyl positions. Therefore, if you have anything like this, NBS, you will write this as OH here. Sorry, Br here. So bromination would happen at the allylic position. Same way, even if you have toluene and I have NBS, again you will get benzyl bromide here. This is a product you will get. Now, recently in JE, once it was asked, as NBS followed by in water like this. So NBS in water is given. That means N-bromosuccinamide is in water. If it is in water, then you do not make a radical mechanism. That means here you are making it as a Br plus and water will have the OH minus part which will attach. So this is an electrophile, this is a nucleophile. So basically the addition what you are getting is OH here and Br here. So this is the addition we are talking about if it is NBS and water. Okay. At the start of the session, if you notice, there is one reaction I told you that when you have a double bond and if you have a Br2 and CCl4, sorry, this is what the end of the last session. So where you will have Br and Br getting added, this will follow via a bridge bromine bond here like this, a bridge bromine bond. Same way, in case if you have bromine water also, Br2 H2O, then you will get Br here and OH here. So here also it is an anti-addition via bromonium bridge formation. Bromonium bridge formation. And other reactions which will of a similar kind includes BrCl, for instance. Here Br will have plus and Cl minus Cl will have negative charge. The one which is positive will always come here, negative will come at this point. Same way, if you have Br and ICl here, so accordingly you will get this as Cl here and iodine here. Okay. And another reaction of a similar kind is NOCl, wherein NO will have delta plus and Cl will have delta minus. So here we'll get NO and here we'll have Cl. Okay. These are few reactions. First we started with NBS and how the similarities is observed when it comes to electrophilic addition. The next reaction includes ozonolysis. Ozonolysis, it is basically an oxidation reaction. So in case if you have a CH2 double bond CH2 and if you treat that with ozone in the presence of zinc and water, this will give you an aldehyde form. So like this, so you basically break it, double bonds here, so we will have this hydrogens present. So basically 2 moles of formaldehyde is what we get. This is called reductive ozonolysis. Reductive ozonolysis. Okay, clear. While if we have O3 in the presence of directly I have been given water or H2O2 or both. So in that case, first it will get 2 moles of aldehyde, but this aldehyde will get further oxidized to convert into acids, HCOOH. Clear? So we will get this as HCOOH. In fact, HCOH can also be further oxidized to convert into carbon dioxide, but most of the time the ozonolysis is occurring at a very low temperature. So formic acid is where you will end the reaction. Got it? Now this is called as oxidative ozonolysis. oxidative ozonolysis. Okay. As much as mechanism is concerned, what you need to know is that CH2 double bond CH2, basically ozone will have like this O with minus and plus. So pi will attack here, this minus will attack here. So that will first form a compound called molozonide like this. This is called molozonide. Clear? Molozonide is, an unstable form here, which will convert into, basically carbon-carbon bond here will break and this oxygen will be introduced above here. So if you notice that, this is what you will get, CH2, CH2 with an oxygen and other two oxygens connected this way. This is, ozonide. Ozonide. We'll get an ozonide form. Okay. And from the ozonide form, we will be able to get the next product. That is, here the bond breaking will take place like this. So as the bond breaking happens, you will get 2 moles of aldehyde and a nascent oxygen. And that nascent oxygen is what is getting controlled by zinc. Okay. So this is about ozonolysis. So as much as ozonolysis is concerned, I think uh, uh, your focus should be only on understanding what is oxidative and reductive ozonolysis. Bond breaking wise, I'm sure you do understand what would happen. Okay. Right. So typically question how it is being asked is, generally you will be asked the compounds given and you need to find out the reactant. So for example, this is a very standard example. Okay. On ozonolysis, products, what you will get is propanol and acetone. If it is propanol and acetone, just check out their basic structure here. Propanol is like this one, and acetone is like this. So just include those two and make a reactant. So reactant is the question what is being asked. So what will be the reactant in this case? The reactant would be like this. So you must have a double bond here this way. So only when you break this bond, you will get these products. So this is a very standard question that is being asked. Otherwise, more examples from ozonolysis is about benzene, how it breaks down. Benzene, if you react with O3, you will get 3 moles of glyoxol. And whatever I'm doing is in reductive ozonolysis, right? Similarly, in case if you have xylene, xylene has actually two resonating structures, and both resonating structures might give you two different forms. So this O3 and zinc. So here one product what you will get is double bond O and H plus 2 moles of uh, glyoxal. And when you break out on the other side, you might also get this one. So basically overall you will get 3 different types of products, not the number of moles. The types of products are different here. Got it? Okay. So this is how typically it can be asked. Next. The next important reaction in hydrocarbons is Birch reduction. Okay. What is Birch reduction? Birch reduction is when you have, alkynes reacting with sodium in liquid ammonia. This also I told you earlier. So just recall it once. Here you will get basically an alkene which is of trans form. So it will have a trans molecule. Clear? So usually this is blue in color, and after the reaction the color will be fading out. Okay, sodium in liquid ammonia is usually blue in color. Okay, so it will not be giving any reaction with a terminal alkynes. So if you have a terminal alkynes, okay, with liquid ammonia, you will not get an alkene. You will only get it like a salt here plus H2 of H2. This is what you will get. Okay. But if you have a alternative double bonds, then the reaction would take place. Sodium in liquid ammonia. This will make an hydrogen added at two ends here. So one hydrogen will get added here. So like this, we can have one hydrogen getting added here and the other hydrogen getting added here. So this is how the product will get. So basically 1,4 addition can happen on the conjugate side. And the conjugation can be observed even on benzene. So that's why when you react benzene in liquid ammonia, you will get conjugated addition of 1,4. So you'll get one hydrogen here, and now you will get an isolated dienes. You'll get this isolated diene as a product. Within that, there is a application that by chance if you have CH3, here CH3 is an electron donating group. So by chance if there is any electron donating group and then you react liquid ammonia, then you will get a double bond formed like this, isolated double bond forms existing this way. But if you have a withdrawing group like COOH, which is electron withdrawing group, okay, so in that case with Birch reduction, sodium in liquid ammonia, this will give you isolated double bonds this way. Again, don't get into the mechanism part, just remember electron donating groups, you will put it slant double bonds. Electron withdrawing group, you get vertical double bonds. Okay, so this much information is what you essentially require for uh, Birch reduction, correct? In fact, last thing we can also do it for naphthalene. So suppose if you have a double bond like this here, if sodium and liquid ammonia is given, so in this case you will get this added and H will get added on this position. Okay, right. So this is about the Birch reduction, guys. Right, next, if you notice hydrolysis of carbides, that includes calcium carbide on addition with 2 moles of H2O, so that will convert into calcium hydroxide, and C2H2. C2H2 basically is acetylene. This is the product that is formed. Mg2C3 on the other hand, if this undergoes hydrolysis, and here we'll get 2 moles of magnesium hydroxide, plus you will get this as CH3 C triple bond CH. Okay, this is the major product. Similarly, B2C, okay, or Al4C3, beryllium and aluminum will have diagonal relationship. So if you react with H2O here, so you can get beryllium hydroxide or aluminum hydroxide and ending up this with methane. So you will get this as methane. This is about the hydrolysis of carbides. Got it? So as much as carbides is concerned, only this much part you need to know. Clear? Next reaction is about heating with, red hot iron or copper tube. What are the respective reactions in this case? See, if I take 3 moles of uh, acetylene here and you take red hot iron tube, so that will convert into benzene. Got it? If I take 3 moles of CH3C triple bond CH, which is propine, the propine will convert into mesitylene. This is mesitylene. Okay. If you have 3 moles of, substituted alkynes here, so that would make it, you know, complete methyl groups on benzene, 6 hexamethyl groups. Okay. This is what happens with red hot copper tube. Clear? See, electrophilic addition can also take place here. So we will have CH3C, sorry, let me write down that. Electrophilic addition here. So if you have triple bond CH with HCl, well, the mechanism is not generally like this. It is not going to happen as if there is a first carbocation forming and then Cl minus attacking. This is not how the mechanism take place, but the product type is same. Again, I'm not getting into the mechanism how it happens, but the product nature is the same, which means first you will get C double bond CH2 and Cl following Markovnikov's rule. Markov rule is followed. And you know that once you get here CH3, C double bond CH2 and Cl, again if you add with HCl, you will get one more chlorine on the same position as earlier where the chlorine was, again following Markovnikov's rule. Okay, this is following Markov rule. Clear? So this is how the addition would take place. Two chlorines, two bromines, two halogens, everything will come at the same position here. Okay. Next, in case if you have water also, let's say, suppose I have CH3C triple bond CH with one equivalent in H2O. Correct. So in that case, CH3C double bond COH will be there. Okay, sorry, Cl will be there here. Okay, and OH will be added, just like how we do it in a double bond addition, same thing. But this will undergo tautomerism. To undergo this as CH3 C double bond O CH2 Cl. This is with one equivalent. If you do it with two equivalent or excess, correct? So in that case, so what do we get? First you will get CH3 COH double bond CH and Cl. You do one more addition with this one. So if you add one more addition here, so that is if you have HCl here, so that will undergo addition and finally converts into CH3C, two OH groups. Two OH groups will again convert into ketone, but this time there will be two chlorines added. So that is a final product you should report. So CH3C double bond O, CH, Cl and Cl. So this is the difference you need to notice. One chlorine here, while in this case we'll have two chlorines here. So that is a product form that you need to remember. Got it? Next, what is the test of alkynes? What are the test of alkynes? See, alkynes mainly have two tests. One is Tollens test. Tollens test. Tollens test is, what we use the word silver mirror test, but this is not a silver mirror test. Okay, this is just a Tollens test, but not silver mirror test. The reagent used here is silver nitrate in the presence of NH4OH. Okay, and the reaction is like this: CH3C triple bond CH. It is only for terminal alkynes, so there has to have a terminal alkyne that when you react with AgNO3, correct, in the presence of NH4OH, this will convert into an silver salt Ag plus, okay, uh, that plus H2, half H2. So this is a product you will get. Correct. So what we are getting here is a white PPT. You'll get a white PPT. Same way, just like Tollens test, we can also have, uh, cuprous chloride test also. Cuprous chloride test. So cuprous chloride test is CH3C triple bond CH when you react with Cu2Cl2 in the presence of NH4OH. Okay, in the presence of NH4OH. Now this will give us CH3C. Okay. Now here triple bond C minus and Cu plus. Now this is brick red precipitate. So red PPT, clear, plus half H2. So this is the product you will get. Now the another interesting fact here is, if I take 2 moles of CH3C triple bond CH plus Cu2Cl2, but this time in the presence of NH4Cl, then instead of going for this reaction, it will go for a dimerization. So you will get something like CH3CH double bond CH, which is connected to C triple bond C CH3 this way. And if you follow this through with dry HCl, if you add dry HCl, it will become CH3 CH double bond CH with C Cl here, correct, with double bond C and CH3. Okay, double bond CH here, so double bond CH and CH3. Okay, this is how the addition will take place. To write this reaction again, suppose if you write the same reaction with uh, uh, alkyne, so this, if you react with Cu2L2 in the presence of NH4Cl, so 2 moles of that will convert into CH triple bond C with CH double bond CH2. And then when you react this with dry HCl, you will get this as CH2 double bond CCl with CH double bond CH2, just like addition. So basically what you have is a conjugated diene. So you'll end up having conjugated diene. Clear? The name of this is called chloroprene. This is called chloroprene. Okay. So chloroprene is an important monomer to making a polymerization. Correct. So this will give you an artificial rubber. So if you take a suitable catalyst, okay, and heat it here. So if I take n moles of this, so basically you will get this as CH2, okay, with here getting into Cl with double bond like this, CH double bond, and then we have CH2, and this will extend into N, right? So this is a polymer which is formed, and this polymer is called as neoprene. Neoprene is nothing but an artificial rubber. Artificial rubber. So all the cycle tires, car tires, or auto tires, they are all made up of neoprene. Correct. So this is another important reaction which you need to know. Okay. So overall, if you ask me, as much as hydrocarbons is concerned, I'm only talking about alkynes, alkenes, and alkynes. These many are the reactions that you need to know. Okay. Thank you.